Whoops, sorry. Hi, everyone. This is the quiz review for sections 9.6 and 9.7 for Algebra 2. And this is pretty heavy stuff, so I thought I'd put together a video of just kind of working through these problems and showing you my plan of attack for each one. So I'll probably do two videos. This first video will just be the front page 1 through 4, and then I'll do another video for the back page, just so it's not too long. So this first question. Write an equation in standard form. So the first thing I want to point out is standard form indicates that I am going to have to multiply this all out, meaning I can't leave it in factored form. All right, that's sort of the difference, standard form versus factored form. Of least possible degree just means, no extra numbers, and you'll see what I'm talking about in just a minute, but just trying to decode a little bit for you. With these roots, okay? And the really big important connection to make here is between roots and factors. Every time I have a root, I can turn it into a factor. So I can turn this into x minus 2. I can turn this into x minus 3i. But then just remember that those non-real roots, the imaginary roots like this one, always travel in conjugate pairs. So even though I only gave you these two, you have to know to add this one to your list. Negative 3i. And so then if I made a factor that was x minus negative 3i, that would really turn into a plus. All right, so that's where the plus is coming from. So right now, technically, that is a polynomial. All right. And so the least possible degree means I just don't have any other numbers floating out here. It's just going to be plain old x's here. I don't have any multiplicities. All right, that's the other thing that I should have put up here. None of my roots are multiple roots, okay? But if it wants it in standard form, I do need to simplify this. So because I know this is going to work out really nicely, I'm going to start by multiplying these two. And we've done enough of these that you might be starting to get what this result will look like, but x times x is x squared. I'll put it up here. And then here I'm going to end up with positive 3i x and then negative 3i times x. Because these two things are conjugates, that's sort of designed to make those middle terms drop out, right? Because I'm going to get a positive version and a negative version. So I don't have a middle term here, but then I'm going to end up with negative 9i squared, which I could then replace with a plus 9. Okay, because I squared is negative 1. So negative 9i squared becomes a plus 9. And now I'm doing that x squared plus 9 times my x minus 2 from over here. So x minus 2 times x squared plus 9 is going to give me, let's see, that'll give me an x cubed plus 9x minus 2x squared and then minus 18. Okay. And I sort of ran short on space there, but that would be my polynomial in standard form. I'm lying a little bit. Technically, standard form, these should be in the opposite order. I should have my x squared first and then my x. If I had more space, I would rewrite this thing, but as long as you can get to this part, I think the switching pieces around at the end is not too bad, okay? Okay, so let's take a look then at number 2. We've got this crazy graph, and I just want to clarify, I'll probably mention this in class too, but we are going to assume the graph hits the line right there, okay? So it says, how many real zeros does it have? Real zeros you can always see on the graph. So I see a real 0 here and a real 0 here. So I have 2 real zeros. How many imaginary zeros? So what I would do for this is let's draw a horizontal line anywhere we want. We want to try to hit the graph the maximum number of times. So I see 1, 2, 3, 4, 5, 6, 7 intersections. Okay, that means I must have at least 7 roots total, and that includes my imaginaries and my reals. So if I have to have 7 total, and I have 2 reals, technically that leaves me with 5, okay? There's a problem there though. Imaginary zeros always run in pairs. Remember we talked about that up above? Okay, imaginary zeros run in pairs. So I can't actually have 5 imaginary zeros. All right, this is always going to be an even number because your imaginary zeros run in pairs. Okay, so the sticking point here, the thing that we're kind of missing, is this guy. Okay, that right there, remember when the graph hits the axis and bounces off? That's a multiplicity. That's a multiple root. Okay, whoops. Which means that we have 2 real zeros, but one of them is a double root. Okay, so that actually accounts for 3 of my 7, and then I would have 4 that are imaginary. Okay, I know that's confusing, but that's a weird one with that multiple root in there. Okay, normally I could just subtract it, but this time when I subtracted, I could see a problem there because my imaginaries have to come in pairs. And then I looked back at my graph and said, oh, wait a second, I have a multiple root there. Okay. Least possible degree then is always just this number. It's how many times did you get that line to hit the graph. Okay. And so I know I must have a degree of at least 7 with this many zeros, and maybe I should just put in here that I have at least 1 with a multiple. Okay. This one has a multiple root for sure. Okay. Sorry, my paper's kind of a mess there. Number 3, build a polynomial with these zeros. And I really like this wording. I like the way they say build a polynomial because that's really what we're doing is we're just putting all these things together. So before I start anything, I'm going to scan down my list and look for my imaginary roots and make sure that I have their partner, right? So if 5i is one of my roots, I have to add negative 5i to the list. And it's going to have a multiplicity of 3 just like its partner does. Okay? So now I'm going to turn each one of these roots into a factor. Okay? And then once each one of them is a factor, I'll give them their multiplicity. So, and remember it's always x minus whatever the root is. Okay? So if I were to do x minus negative 2, that's really going to be x plus 2. Multiplicity of 1 means it has a power of 1. All right, x minus negative 1 would give me x plus 1. Multiplicity of 2 means I have 2 copies of that. 5i would be x minus 5i. Multiplicity of 3 means power of 3. Okay, x minus 3/4, we could write that as x minus 3/4 if we want to. Or we could swing that 4 over and make it 4x minus 3. Either one's okay with me. Okay, and that one just has a multiplicity of 1. And the reason it's okay to leave this like this is because we're not really being told that we're trying to match something else. We're not worried about getting a leading coefficient of 4 in there or anything like that. Okay, so that's why it's okay to do this either way. There's actually more than one polynomial that would have these zeros. This just wants me to build one, so I'm choosing to go this route. And then just like up here, if I do x minus negative 5, I'm actually going to get x plus 5 with a power of 3. And so then really, I would just want to write my answer so that these are all being multiplied together. So my final answer would look like this. X plus 2 times x plus 1 squared times x minus 5i cubed times x minus 3/4 times, oh, this isn't going to fit, x plus 5i, also to the power of 3. Okay? And that's really it for that one. It doesn't say, thankfully, it doesn't say that we had to do it in standard form like we did in number 1. So we don't have to go through and multiply those because that would be miserable. Okay? But we're good on that one. Okay, and number 4. So here's a function. They kind of are giving us a function similar to what we came up with up here. All right? What is missing? That's where I'd be on the lookout for something like this. Okay? Make sure all your imaginaries have partners. So as I skim through here, that's going to be real, that's going to be real. Oh, this right here, a minus 3i, means that I should have an x plus 3i in my factors as well. Okay? This one and this one, both of these might have imaginary roots, but because they've got x squareds in them, both copies of that imaginary root are included already. So really the only ones you have to look out for are any of them that actually have I in them. Okay, so what's missing? I should answer that down here. We're missing a copy of x plus 3I. Okay, before I talk about part B, let's go ahead and do part C, because I think part C is we're going to list everything, and then we're going to pick some off the list that would be x-intercepts, okay? So find all the zeros. Anytime you're finding zeros, you're taking the factors and setting them equal to 0 and then solving. Okay. So I'm just going to list all of those real quick. I'm going to do 4x equals 0. I'm going to do 3 minus 2x equals 0. And notice that one had a multiplicity of 2. I'll deal with that when I write down my answer. All right, x minus 3I equals 0. X squared plus 25 equals 0. X squared plus 3x minus 2 equals 0. And x plus 3I equals 0. When you're doing this on your own, you may not actually need to write all of those out, but I really just wanted to make sure you could see what I was doing here. All right, so if 4x equals 0, and I divide each side by 4, I get x equals 0. That's one of my roots, and that one only has a multiplicity of 1. 3 minus 2x, so I would subtract 3, so that gives me negative 3 over here, divide by negative 2, and I end up with x equals positive 3 halves. And that one came from right here where I had a multiplicity of 2, so I would say that this root has a multiplicity of 2. Okay? All right, if x minus 3i equals 0, then I could slide that 3i over and get x equals 3i. And that one didn't have any multiplicity. This one, x squared plus 25 equals 0. You could do quadratic formula here. I would probably just subtract the 25. So I would get x squared equals negative 25. And then take a square root, and I would get x equals plus or minus 5i. Don't forget, when you solve with a square root, you need a plus or minus. Okay? And that takes care of both partners, right? Both of my partners are included there, plus or minus 5i. Okay, to solve this guy, set equal to 0, that's a quadratic formula problem. Okay, and again, we could have used quadratic formula here, but we did have a shortcut. Get all this junk out of here. Oh, quadratic formula, I have 1, 3, and negative 2. Okay, so these are irrational. I'm just going to put them down because it doesn't say I need exact answers. I'm just going to say x is approximately equal to 0.56 and x is approximately equal to, negative 3.56. And that one also did not have any multiplicities. And then x plus 3i equals 0. Slide the 3i over and you get x equals negative 3i, which is good because now this one has a partner. Okay? Just before I go back to question B, take a look at all of the different roots you came up with here. Because one of the questions that's going to come up on something like this could be, what's the degree of this whole thing? Okay? Thank you. So remember that the degree always has to match the total number of zeros, including all the multiplicities, right? So if I was asked what's the degree of this thing, I mean, I certainly don't want to try to multiply this all out, okay? But I can count. I can count zeros. So I have 1, 2, 3, because that has a multiplicity of 2, 4, 5, 6, 7, 8, 9. So that tells me that my degree on this polynomial would be 9. Okay? If I asked you, that question didn't actually come up here, but I know that it's going to come up on your quiz. Okay? And I've seen some people try to multiply this out and it's miserable. Don't do it. So now the question is, how many x-intercepts does the graph have? And this is another thing. I've had people try to graph this and actually look at it. Oh, that's miserable too. Okay? the x-intercepts are going to be anywhere you have real roots. So your imaginary roots will not actually make x-intercepts happen, right? Because it won't actually cross the x-axis. And then if there's a multiplicity, that's someplace where it's just going to touch the x-axis but not go through. That still counts as an intercept, but you don't count it as like a double. Okay, so we don't really include multiplicities here either. So in terms of counting up my x-intercepts, all right, if 0 would be an x-intercept, 3/2 would be an x-intercept, but I only count it once. That's imaginary. That's imaginary. These aren't, they're not pretty, but they are real. Okay, these are actual places on the x-axis that we would cross. And then that's imaginary. All right, so I have 1, 2, 3, 4 x-intercepts. Okay, so again, x-intercepts are any of your real roots, not including your multiplicities. All right, if you think about where this is physically going to cross the axis. Okay, I'll go ahead and put together another video with the second page of this, but hopefully that helps out a little bit with the first.